Good day all, I'm Uche Osahor. I'm co-advised by Nasser Nasrabadi, and the topic is Ortho-Shot low displacement rank regularization with data augmentation for few-shot learning. Introduction. In few-shot classification, the primary goal is to learn representations from a few samples that generalize well for novel classes. We propose an efficient low displacement rank regularization strategy termed Ortho-Shot. Our technique imposes orthogonal regularization on the convolutional layers of a few-shot classifier, which is based on the doubly-block toeplitz matrix structure. With comparing results, we demonstrated that a DBT-based low-rank orthogonal regularizer with data augmentation significantly improves the performance of a few-shot classifier. Our motivation divided into two categories. We have regularization and augmentation. For regularization, basically in feature classification, the primary goal will be to learn representations from a few samples that generalize well for novel classes. And so the regularized convolutional layer of the feature classifier tends to enhance model generalization and intra-class feature embeddings that are crucial for few-shot learning. And also for augmentation, overfitting is kind of a typical issue for most few-shot models. The lack of data diversity inhibits proper model inference. In that regard, we broke down the pipeline of the few-shot classifier and established that the support query and task data collectively alleviates overfitting in networks. This is an example here. We show for the doubly-block toeplitz structure, we give the space and time complexity representation for different approaches. We have the toeplitz here in green, which shows the best and most efficient structure to use. Here we give the DBT matrix structure, and we have the dimensionalities for both the row orthogonality and column orthogonality. And we have the number of kernel size, which is 3 that we used. Our model architecture is basically contains embeddings that are regularized based on the DBT structure matrix. The dotted box here of the CNN block illustrates the inner translation between the convolutional layer embeddings and the more efficient DBT-based embeddings. And within the layers, we regularize these layers to improve the overall performance of the few-shot classifier. Here we show the lemma that shows the row orthogonality and the equivalence to the column orthogonality, which we use to establish L-orth as the loss for our orthogonal regularized few-shot model. Here we show accuracy results for training and validation on an R2-D2 based learner with a DBT regularized ResNet backbone on the CIFAR-FS dataset, which are in the top left, and the top right model using augmentation and the max-up. So here we show our baseline for both train and validation, and here we have for augmentation using the max-up for both training and validation. Here we also showed accuracy results for on-query augmentation for the baseline, the cut mix, and the max-up. For this first plot, we see the wide generalization gap, which is obvious because we have not implemented any form of augmentation. However, when we have augmentation included with the max-up technique, we see a shrinkage generation gap between both training and validation, which is quite impressive. In the case here also, we have accuracy results when we use a query augmentation, and we see the performance supersedes when we have test on query or no query augmentation. So query here represents the query data. On the other side here, we have model accuracy plots for the CIFAR-FS and miniImagenet databases on both CNN and DBT model baseline with augmentation and without augmentation for both 5-shot and 1-shot cases. In conclusion, our approach was aimed at maintaining the stability of activations, preserving gradient norms, and enhancing feature transferability of deep networks. We also broke down the pipeline of a few-shot learner, and based on our findings, we established that 3 augmentation strategies that aid in minimizing overfitting and increasing data diversity. Our findings and empirical results confirm that a DBT regularized model is beneficial to feature classification and meta learning in general. Thank you.